Now that we've given an overview of some of the number systems that we've been looking at and some of the issues that we're going to be dealing with rings, we're going to talk a little bit more specifically about arithmetic axioms, in particular for integers. So we're going to list the arithmetic axioms that we're going to assume for the integers. We're going to prove a theorem using those axioms. We're going to discuss what the difference is between assuming axioms about something and actually defining it, in particular for the integers. We're going to talk about why we have axioms at all and what makes a good set of axioms. All right, so for the arithmetic axioms, these are almost all, or probably actually completely all, going to be familiar to you. So first of all, the set of integers has two arithmetic operations, namely addition and multiplication. There are kind of two more, subtraction and division. Division has some closure issues, and subtraction we're going to deal with in a different way later. But the nice thing about addition and multiplication is that the integers are closed under both of those. So whenever we add or multiply two integers together, we get another integer. Addition and multiplication both have the nice property of commutativity. They're both commutative, which means that if we take any two integers and add them together in either order, a plus b or b plus a, we get the same result. Same thing with multiplication. A times b is equal to b times a. Addition and multiplication have a property called the associative property. And before I explain that, I should really emphasize that addition and multiplication is really an operations between two numbers at a time, right? So I can only add two numbers at a time. I can multiply two numbers at a time. So then the question is, well, what does it mean to add three numbers at a time or multiply three numbers at a time? Well, we can do that in two ways, right? For addition, for instance, we can either add the first two, take that result and add it to the third, or we can add the last two, take that result and add it to the first. Well, it turns out with the associative property that doing either of those gives you the same result. So a plus b plus c is equal to a plus b plus c. And similarly with multiplication. A times b times c is equal to a times b times c. The set of integers satisfies the distributive property. And in particular, the distributive property called multiplication over addition, where if you have three numbers, a, b, and c, a times the quantity b plus c is equal to ab plus ac. There is also something called an additive identity. Whenever we talk about an additive identity, identity means we're leaving things alone. Additive means we're leaving things alone through addition. And so an additive identity is some number b, such that whenever you add b to any number a, it leaves it alone. In other words, a plus b is equal to a, leaves it alone, or b plus a also equal to a. Both of those are true. We're going to eventually call that additive identity 0, but first we have to deal with the hypothetical issue of, are there any more additive identities other than the 0? Right? We can't say 0 is the additive identity until we've established that there's only one. Similarly, we have a multiplicative identity, and that's a number that leaves all other numbers alone when you multiply it. So there's some number c where when you multiply c on either side of a random number a, it leaves it alone. A times c is equal to a, c times a equal a. And as with 0, we're going to eventually denote the multiplicative identity by 1, our very familiar number to us, but as before, we have to deal with the fact that we might have more than one. Logically. Turns out we don't, but we got to prove that. Next, we're going to talk about inverses. Now, inverses, whenever I talk about inverses, those are things that cancel out. So what do I mean by an additive inverse of a? It means a number that cancels it out additively, which means when you add it, you get the number 0. You get the additive identity. So if we have an additive identity b and any random number a, then another number d is going to be the additive inverse for a if when we add it to a, we get back to the additive identity, and that's on either side. Now, again, eventually b is going to be 0, and eventually we're going to call d negative a, right? But we can't call it negative a because, well, you guessed it, we don't know if there's more than one additive identity for a given number. We believe it, We believe it in our bones, but we still have to prove it. All right, so now let's go ahead and try proving a theorem. If we have two numbers a and b in the integers, if negative a is an additive inverse for a and negative b is an additive inverse of b, then the question is, what is an additive inverse for a plus b? All right, so we're going to fill in that blank after we play around for a while. But like with lots of theorems, we may not know what the answer is. We may pose it as a question and then figure out the answer, and then that's our theorem. All right, so first of all, I'm going to dispense with some of the issues that we will deal with in our in-class activities. We're going to prove that there is just one additive identity, so we're just going to call it 0, right? We'll do that now. You'll prove that later. Thanks for helping me out. And I just want to remind you what the definition of additive inverse means in this context. So if negative a is an additive inverse of a, that means exactly a plus negative a is equal to 0. And for negative b to be the additive inverse of b, that means precisely b plus negative b equals 0. So if we want to find the additive inverse of a plus b, we got to find a number that we can add to a plus b to give us 0. And once we find that number, that's what we're going to put in our theorem. Well, let's see. So in order to cancel out a plus b, we got to cancel out a. We got to cancel out b. Negative a cancels out a. Negative b cancels out b. So negative a plus negative b seems a really good candidate for the additive inverse of a plus b. How do we know? Well, the test is going to be, if we add that number to a plus b, do we get 0? If we get 0, it's an additive inverse. If we do not get 0, it's not. All right, but we believe it, right? So we're going to put it in our theorem very confidently. So negative a plus negative b is an additive inverse for a plus b. And if you didn't see what I just did there, I just changed the theorem at the top of the slide to indicate that that's what we're going to try to prove. All right, so in other words, the additive inverse, the negative of a plus b is equal to negative a plus negative b. All right, so again, in order to prove this, we've got to take a plus b, add negative a plus negative b to it, and see if we can get 0. All right, so the first thing I'm going to do is I'm going to note that a plus b, same as b plus a. So I'm just going to replace a plus b with b plus a, and it turns out that's going to make our lives a little bit easier. And now and that's by the commutative property, of course, right? A plus b is equal to b plus a, the commutative property of addition. Now I'm going to use the associative property to rearrange the parentheses, right? So I get b plus a plus negative b. And again, I can do this. I can rearrange those parentheses because of the associative property. And now we're in a really nice position because a plus negative negative a is the additive inverse of a. So negative a plus negative a is equal to 0. Again, that's by the definition of additive inverse. And now we have b plus 0. 0 is the additive identity. It means it leaves things alone when you add it. So b plus 0 is equal to b. So I'm going to replace b plus 0 with b. And that's the definition of additive identity. And now I have b plus negative b. Negative b is the additive inverse of b. And so when we add that to b, we get 0. And that's the definition of additive inverse. So what have we just shown? We've just shown that a plus b plus negative a plus negative b equals 0. By definition, that means negative a plus negative b is the additive inverse of a plus b. And that completes our proof. All right, so now I want to talk about a little bit more foundational question with respect to axioms. So we have a bunch of arithmetic axioms. The question is, do these arithmetic axioms define the integers? And that is a tricky question. Well, not that tricky. The answer is no, okay? But it's tricky to explain. So let me give you a few reasons of why that is true. First of all, of the axioms that we just listed, there are many number sets that have these exact same properties, right? In particular, if you go through those properties and compare them to what we have with rational numbers and with real numbers, those satisfy all those axioms. Right? So even if we believed in using axioms to define the integers, it does not uniquely define the integers. We need more axioms to rule out the rational numbers and the real numbers. The other thing is that axioms don't tell us that the integers exist. They describe the properties that the integers have. right? They describe what the properties are, but they do not justify that they exist. So they are descriptive rather than constructive. They help us describe what integers are like if we believe in them. They do not tell us how we would actually build integers from the ground up. If we really wanted to do that, which we're not going to do in this class, but we could, and if you have questions about that, I'm happy to discuss those with you. You need something called Peano's axioms, which would help us construct the natural numbers, and then you'd use natural numbers and some additional definitions to construct the integers. However, for our purposes, we're going to accept that the axioms are going to be true, and we're going to use them to prove theorems about integers. Now, taking a step back, why do we need axioms in the first place? Well, the thing about math is you cannot prove anything without assuming something. If we don't have axioms, which are the things that we assume without proof, we literally can't prove anything. Without axioms, we just can't do math. The next question, of course, is how do we know what axioms are appropriate? Well, axioms are choices. We have to choose them, right? Which means that they are fundamentally subjective, right? And that means that maybe we argue about which axioms we include and which axioms we don't. So some general guidelines is they should be reasonable. And again, reasonable for me, reasonable for you might be different. So we have to sort of negotiate those things. Mathematicians should be able to agree on them. If not, then that just means that the axioms are unsettled, right? And this can sometimes be tricky. If you've ever heard of the axiom of choice in set theory, that was one of those things that used to be controversial. I don't know if it is now. Maybe it still is. They should definitely not contradict one another. If you have contradictory axioms, that means that you can literally prove anything, and that is a terrible axiomatic system. You shouldn't be able to prove literally anything, even things that we consider to be false. There should probably be few as possible. And in particular, we should not be able to prove one of the axioms using the rest of the axioms, right? That would be completely redundant. All right, so now that we've discussed this, it's time for you to look at some of the problems and proofs that we have for arithmetic axioms. That's on the PDF file that is included with this video.